Okay, so we were talking about the bending moment diagram. So we have here, as we said, the slope is decreasing. We have a downward concavity. Now, concerning the values, we start by a negative value because we have a counterclockwise moment. We start by minus 5 omega L square over 4, which is equal to the reaction at fixity. Now, from 0 to L over 2, what is happening is that we should look at the area under V curve, okay? Because the area under V curve will be equal to the increase in moment. So I will look at this area, okay? Now here, how to calculate this area? I will divide it into two parts, in a rectangle, okay, and a part of parabola. So for the rectangle area, so I can say that the whole area is A1 plus A2. So total area here is A1 plus A2. A1 is the area of the rectangle. Okay. So here this is A1 for the rectangle. A1 is equal to, we know that the length here is L over 2. So it's L over 2 times the width of the rectangle here, which is, or height, which is omega L over 4. So times omega L over 4. So A1 is omega L square over 8. Okay. Now, concerning A2, A2 is this area for this part here. Okay, this part. This is A2. I will remind you of a certain theorem for a parabola. If you have a parabola, okay, and the condition to apply this theorem is to have a horizontal slope at one of the points of the ends, okay, or here or here. So you have here a parabola. Whenever you have a parabola having a horizontal slope at one of its extremity, okay, then if you know that this distance is A and this distance here is B, then you can say that the area here, the small one, yani this part, because you have a small area and a big area, because if you complete your parabola, so here, okay, you have two parts for your parabola. The part below the parabola and the part above the parabola. This part here is, the area of it is 2/3 of AB. And this part here is 1/3 of AB. Here we are interested in the lower part. So this is AB over 3. In our case, A2 is equal to, here the value of B is L over 2. The value of A is this part, okay, which is omega L over 2 minus omega L over 4. So it's omega L over 2. So omega L over 2 times L over 2 over 3. So it is L over 6 if you want. Okay. So you will get that A2 is equal to omega L square over 12. Okay. And now you can say that A1 plus A2, so delta M if you want. So delta M between these 2 points here. So in this part, okay, you can say that delta M is equal to omega L square over 8 plus omega L square over 12. Okay. So you can get the value of omega here. you can just do this value you obtain plus minus 5 omega L square over 24. You will get minus omega L square over 24. So at this point, this is the value of the moment. Now, just one thing. Sometimes your area is like this, and if you have the parabola, the inverted parabola like this, then the area you will consider will be 2/3 of AB. Okay, in this case, the horizontal slope will be from this side. So this area here will be 2/3 of AB. Okay, so it will depend on your figure. How is the concavity of shear will determine which formula to use. Okay, so now in the other part, first concerning the variation of m delta m, it's equal to A3, the area of this triangle, of this part of the parabola. Okay, and A3 here is equal to A1, sorry, A2. Okay, why it's equal to A2? لأنه we have the same height, which is omega L over 4, and the same length here, which is L over 2. So you'll get A2 should be equal to the value of, so A3 equals to A2. Okay, it is just here, guys. Here it is omega L over 4. Let me fix it for you. لأنه the width here, okay, is the width here. It's not omega L over 2. It's omega L over 4, because it's omega L over 2 minus omega L over 4. So this part here is omega L over 4. Okay. This is why when in the calculation of A2, I should put here over 4. So this is over 24, okay? And here it is 24. Okay. So now I can say that A2 equals to A3 equals to omega L square over 24. So since my moment was minus omega L square over 24, I should add to it plus omega L square over 24, and I will end by 0. And this is also expected. So if you get a value different than 0 at the end of your beam, then you have a calculation error somewhere, so you can fix it. Okay? So here, why it should be 0? Because if you go back to your beam, you don't have any couple at the end of your beam. No reaction, no couple, no fixity, no couple here. So the bending moment should end by 0. So as expected, the shear and bending moment at the end of my beam are equal to 0. Okay? Any question on this? Okay. So as you can see, it's one technique. Once you know well the technique, it's the problems are very simple. Another problem, draw the shear and bending moment diagrams for the following beam. So here you have a beam. The beam is subjected to a distributed load, and at its middle also we have a concentrated force. Okay, you have a pin at A and a roller at C. We know that it's a roller at C because of, let me zoom it a little bit, because of the small rolls here. Okay, so the first step, as usual, is to determine the reactions at A and C. At first, no loading in X, so you can say that AX is 0. In general, when you have symmetry, this will facilitate your calculation, because look, due to symmetry in loading, I can say that AY is equal to CY. Okay, so, and it's equal to the load over 2. Okay, And if you do sum of y equals 0, you will get 2 times ay or 2 times cy equals to 40 times 4, which is 160, minus 20, so 140. Then the reaction at y and at a and at c is 70 kilonewton. Okay, so if you pay attention for symmetry, you can instead of doing two equations, you can get it directly from one equation. So now we know the value of the reactions, we can start to draw the diagram. I already told you as a remark last time, if you have a symmetrical load, you expect that the shear at the middle will be 0. And how to judge that the load is symmetrical? You should have, when you have a beam and you have symmetrical loads, and at the two ends you have same support, and same time of support. Here it's here a roller, okay, but you don't have any x load, so it's symmetrical because you have only y components. Okay, so due to this, you have a symmetry in shear. And even if you have an x component, if you have an x component here, it will just affect it's the value of ax, and the value of ax will not affect shear, it will affect the normal force. So since I have symmetrical loading and I have as supports at the two ends same time of load in y, so I have here a pin and I have here a roller, so I have an upward reaction for both cases, then it's purely symmetrical. So if you have a fixity, for example, here at A, so no, it will not be symmetrical because at the other end you don't have anything. Then the shear at the middle will not be 0. Okay? But here you have symmetry and load, symmetry and support reactions in Y. Then we can say that at the middle of the beam we can expect to have a 0 shear. Okay? And why we have this? Okay? Why we have 0 at the middle? Because due to symmetry, half of the load is supported by each of the support. So when you do a cut at the middle, okay, then you will have that this load will, half of the load will be in equilibrium with the reaction. Now, why the graph of shear will be uh, symmetrical with respect to this point? Okay. Why? Because here, look, when you want to determine shear, okay, if you take the left or the right part, so if you remember when we did a cut, okay, when we did a cut, we say that on the left part, the convention is to have a positive shear to rotate clockwise downward, okay, while on the second part, the convention for shear to rotate clockwise is upward. This will justify why here you have symmetry with respect to this point. Because if I do a cut here and I will keep the left part, when I do a cut from the other side, a symmetrical cut, and I keep the right part, the shear should be opposite. Okay? So from here, you have, if you have positive shear here, you should have the same value but a negative shear in the other point. So we have symmetry with respect to the center of the beam, the axis of the center. So it's enough for you to draw variation of shear for the first half, and then you can deduce the variation of shear for the other half by applying the symmetry about this point. Okay? So here, let us do it for the shear. So to start with, I have an upward reaction at A of 70. So I will start by a value of shear equals to plus 70. Then from A to B, I have omega constant. When omega is constant, this means that V is linear. And since omega is downward, then then V is decreasing. Okay, so I can say that I have the slope here equal to minus the value of omega, which is 40. So the slope is minus 40. And as I go from A to B, okay, I am the variation of shear is equal to the area under this curve. Okay, The area under this curve is 40 times 2, it's 80. So I will go from plus 70 to minus 10 because 70 minus 80 is minus 10. Okay. Now at B, just at B, I have a jump of 20 kilonewton because it's an upward force. So as you can see, I will pass by 0. Okay. So this is the symmetrical point. Now you can directly deduce the other part from symmetry. Okay, with respect to this point. So you can just do this. No need to continue. You can say that the value here is minus 10, the value here will be plus 10, and you know it from the jump of 20. Then since the value here is plus 70, the value here will be minus 70, and you get your diagram. Okay, we will continue with the moment diagram of this problem next time. Any question on this? Okay, so see you next time. Bye bye. And happy Easter.
Thank you.